Yeah, so we'll start now.
Yes,
Yeah,
yes,
we
I
can
think we should start.
Okay, sir. Very good morning and a warm welcome to all of you. Today, 11th is a special day for Indian science and technology, named as National Technology Day, to commemorate the successful test of our country's indigenous technologies, for which we always feel proud. The successful nuclear test at Pokhran, Rajasthan, which is named by Operation Shakti or Pokhran 2, Hansa 3, an indigenous aircraft flown by National Aeronautics Laboratory at Bangalore, and the successful test of Trishul missile on the same day too. Really, this is an inspirational day for all of us to transform India through technology. And of course, the current pandemic situation realizes the importance of science and technologies. To grace this special occasion, we have with us a renowned scientist as well as a technologist of the country, Padmashri Professor Ganapati D Yadav, as our chief guest. And it's a great privilege to welcome you, sir, on behalf of our CSIR-IMMT Bhubaneswar. And we have with us our respected director, Professor Sudhasutto Basu. Now, to move forward this event, may I request our director, Professor Basu, to deliver the welcome address and introduce the chief guest. Thank you. Sir, please.
Good morning to all of you, those who are our staff member joining from their offices or home through MS Teams as we are under partial lockdown. And the friends of CSIR, those who are invited, our guests, director of different institutes, and staff members of different institutes, our own staff members, of course, those who are also present in their office and in a live event. Welcome to all of you on the occasion of National Technology Day. We celebrate every year on May 11, and Dr. Manas Dalai, who is the convener of this program, has already mentioned the significance of the day. I need not, of course, repeat that. We already know about it, but today it is important all of us to associate it with National Technology Day in the form of innovation, dissemination of knowledge, ideating, making new products for the benefit of the humankind. That's what is our motto. In National Technology Day, we should disseminate knowledge and what is going to come up or what new product can come or we can make is what is thus important today, especially at the backdrop of COVID-19, that you have to be innovative and you have to do everything on your own. You cannot depend on your neighboring country or other countries. You have to be self-sufficient. Anything you talk about, whether it's a drug, it's a vaccine, or it's a biomedical devices, whatever you talk about, which we are all experiencing, or supply chain issues regarding, let's say, oxygen generation and supply chain management, or even API of a drug or a vaccine, everything we need to be self-sufficient. That's what taught us in last 1.5 years, that if you are not self-sufficient, if you depend on others in the current pandemic situation, how important it is to innovation and disseminating knowledge and bringing up products. So that is what we have gathered today. And we have a very, very distinguished guest, Professor G.D. Yadav. Of course, I will introduce him to the August gathering. I mean, he's well known, but still I will do that. Before that, I would like to point out, of course, that what the IMMT has been doing in towards this end, which I just mentioned. Of course, IMMT is the Institute of Minerals and Materials Technology lab. We do not do much on bio and on COVID-19, but still in the beginning of the last year, we could do a lot of products like Hasta Suraksha, or hand washing system, or dispensing of sanitizer. Then there was product like coffin, or a automatic dispensing system, or mask, and many others. I'm just not pointing out everything that we did. Those we have made it, and we have of course translated it. We have given the license technology to others. Those who have made the product and sold in the market, we helped many people in the first 3 months of the lockdown in the last year. But today I want to talk that some of the initiative that we have taken last 12 months, especially we are working, as I said, towards Atmanirbhar Bharat, and the rare earth elements are so important in everywhere, whether it is an electronic device or a medical device or a magnet, everywhere, or actuators, sensors. In automobile industry, you require a lot of magnets, and they are specifically they are made of rare earth like neodymium or NdFeB magnets or samarium cobalt magnet. So you have a rare earth like samarium or Nd in this magnets, which is most popular and very good performance. So we are working on rare earth element extraction, and we have recently signed MOU with NALCO, Hindalco, Vedanta, NML, and JNRDDC. 6 partners together going to work on bauxite residue and extraction of rare earth. Scandium is there, lot in lanthanum, scandium, samarium, terbium is there in lot in bauxite residue, and we are working, all 6 of us together. On 31st March 2021, we signed MOU, and we are all working together towards that. We are also working on a fly ash extraction of rare earth and coal leachate. From there, the rare earth we are working, and this project we are working with NTPC, that how some of the rare earth element can be taken out from the fly ash, which is simply a waste. So industrial waste disposal, industrial waste value extraction is what is on our card, and we have developed the technology. Now we are going into the pilot scale. Other technology that we have worked and it is being disseminated is reduction roasting, pelletizing, DRI, that low and lean grade iron ore, which is there plenty in India. And if you have to make 300 million tons of steel by 2030 or 2035, then you require source of iron, and that iron source in India, if you have to import. Otherwise, if you have to use the iron source, which is low and lean grade, this is the technology to move forward through a reduction roasting route. And we are also developing a fluidized based roaster using coal gas, high ash coal, of course, using high ash coal from there to coal gas, and use that coal gas in fluidized bed roaster for fine slimes and the low and lean grade ore. We're working on PMN, polymetallic nodule. This is a program that's going on for a long time, which is a strategic polymetallic nodule with a seabed mineral resources, which is funded by MOES and also platinum group of metals. In the advanced material mission, we have started. This is started by IMMT.
Good morning, sir.
This is started by IMMT, and this is of course curated and coordinated by IMMT along with 6 labs of CSIR, NML, NAL, SICRI, AMPRI Bhopal, CGCRI, and NIST Trivandrum. So we are actually coordinating this advanced material mission of CSIR, while we are working on bio material development, bioceramics development, wearable devices, electrochromic material, optoelectronics material, let's say white LED, meta materials, and such kind of things are happening. The last 2 points I like to mention is IMMT has come up with a CRTDH, Common Research Technology Development Hub, where we will actually help the nearby MSMEs to develop, or those who are already developed to take them to next level of their product. So that CRTDH has come up in last 1 year. Even in lockdown or in the pandemic situation, the building is being has come, and then we are now actually using that, and we are hosting some of the MSMEs. We have equipment as being placed. So the work is going on CRTDH, Common Research Technology Development Hub. Along with that, we have started a InTech, Innovation Technology Enabling Center. This will be our, of course, startups can come here. So This could be our, this is our incubation center. A building will come. We have submitted, of course, for the clarification of our of the doubt of the local municipal corporation to come up to build the building. And we hope that next year the building will be coming up, and this is started functioning, this incubation center, and we'd like to incubate some of the company here in IMMT. We are already incubating at least 4 companies here. We are done, at least 2 of them have done extremely well in the area of mineral processing. So with this information, I try to highlight in today, the National Technology Day, what IMMT taken steps and what are the kind of work we are doing and disseminating knowledge to know our industry friends, those who have joined, to know those who have joined from outside IMMT, and of course, our chief guest, Professor G.D. Yadav, who has kindly agreed to be today's chief guest and the key speakers. Now, I'd like to go to a next phase. I am really very honored to have Padma awardee, Professor Ganapati D. Yadav, as today's keynote speaker. I know him for a long time. He is a great supporter of science and technology. He's a great supporter of CSIR, and he's a great supporter of any scientist around in India and abroad. I mean, right now he has done a lot of work for Indian Institute of Chemical Engineers. Currently, he's president of Indian Chemical Society. Wherever he touches, he brings out a gold out of it. Today, I know that he is working for Indian Chemical Society. I'm just giving you an example. And then today, the Indian Chemical Society journal is being published by Elsevier from this year or from last year. And this is a great thing that he has done. This is a small thing I'm just mentioned, but I would like to formally introduce the speaker, Professor Yadav, who is an Emeritus Professor of Eminence, J.C. Bose National Fellow, Government of India, former Vice Chancellor, and R.T. Modi Distinguished Professor, and Tata Chemicals, Darbari said Distinguished Professor of Innovation and Leadership of Institute of Chemical Technology, Mumbai. And under his leadership as a Vice Chancellor, IICT has expanded. It has got a connection with Bhubaneswar. Under his leadership, he has opened IICT IOC Bhubaneswar here in our city, which is another institute, but of course part of IICT Mumbai, and they are obviously in the backside of our campus. They are doing extremely well. There's one more campus is being also inaugurated and started functioning during his time in Maharashtra. And this is what he has done. This is one of the things that he has done for ICT, which is the expanding ICT in whole of India, and which is a great institute as a chemical technologist, as a chemical engineer, as a chemist, as a physicist, those who are working in the allied areas, chemical engineering, chemical technology like dye, plastics, rubber, you name it, textile, and biotechnology. All these are part of ICT Mumbai, and they have done extremely well. He is fellow of all major academies of India. He is fellow of the major academies of the world. And to name a few of them, he's a fellow of INSA, INA, and all these academies of India. ITWAS Academy, he's a fellow, and he has contributed a seminal contribution in the area, I would say, education, research and innovation in green chemistry, engineering, catalysis, chemical, clean and green technologies, energy engineering, biotechnology, nanotechnology, all these areas he has contributed a lot. And that is how he is a J.C. Bose fellow and fellow of many academies. He is also adjunct professor at the University of Saskatchewan, RMIT University in Melbourne, professor at University of Newcastle, Australia. He of course conferred with Padmashri, as I mentioned, and he comes in the 2% of the world renowned scientists that Stanford University published last year. His rank was 66, and that is remarkable in that category. He has supervised 103 doctoral students, about 125 master's theses, 43 postdocs, and many more. And his H index is he's 62, and he has published many, like there are 3 books, 800 plus special lectures he has given, 470 original research papers he has published, and 109 ICT, PCT is granted, and many more. And so I'm really feeling honored, and I'm also feeling proud that my institute is hosting such a person as a chief guest on a very, very special occasion, National Technology Day, which is celebrated all over India, May 11 every year, and he's kindly agreed to it. And I would really thought that I've spoken to him many times that he would come to our institute, and we will host him in our auditorium, that 600 plus auditorium, and call all people from Bhubaneswar. But today we have all joined because of the pandemic situation through MS Teams or virtual mode. But I'm sure sometime this will end, and one more lecture, not one more, many more lectures are awaiting for him. And I'm sure we are going to host KenCon 2021, and thereafter maybe next year as well. Wherever is possible, take it from me, we will bring him here in our auditorium, and we will have a lecture from him, a popular lecture from him, where we can, people from all institutes of Bhubaneswar can gather and listen to him. But today is a special occasion. I would request him now to deliver his lecture. Please kindly, sir, give your deliberation.
Thank you so much for your kind introduction. And on the occasion of this, can I share this thing?
Yes, please.
Okay, 1 minute. I think there is some issue. Microsoft Teams has a different, So I go here. So this is screen share, right?
Share your screen.
Window. Is it a window? Yeah, I got it. This has got little. So can you see my slides?
Yeah, slide has come, but full screen mode. It has to go to full screen mode.
Sir.
Yeah, no, I will do that. So, on the occasion, yeah, this is okay. On the occasion of this, see, this is typing also. Can we stop that? I don't know whether we can stop it.
Which one?
No typing coming up. No typing coming up here.
Okay, so it is coming for me.
Fine.
Okay, all right. So, thank you so much for your kind introduction. I'm indeed delighted to give this oration on National Technology Day. Perhaps you may not know that this was started by CSIR. Dr. Mashalkar started this series of this celebration of this National Technology Day. And I remember on that particular day, I was in Dharwad. And this was 11th of May, and I was visiting an industry there, and they showed me his letter, and they said, "Sir, we have to start this National Technology Day celebration. Can you give a talk? Luckily, you are here." And I gave a very first talk that day. I remember it very, very vividly. So DSIR and CSIR should take credit for starting this National Technology Day celebration in India. So my greetings to all of you, and I was very happy to know from Professor Basu that IMMT has been doing fantastically very well. I have been associated with your institute since many years. In fact, in 2001, when I was the president of Indian Institute of Chemical Engineers, I had visited your laboratory, and I had known that time director, and also the next ChemCon in 2003 was held there. So I have a very vivid recollection of my association. So congratulations to all of you for developing technology and helping the nation in the pursuit of so-called Atmanirbhar program. What I'm going to do today is I'm going to talk about the so-called net zero issue. And what is this net zero? You might have, known about this climate summit, which was held in April, about 3 weeks ago, where all major nations of the world gathered virtually. And you can see Prime Minister Modi here, Boris Johnson, and Joe Biden of the United States, Angela Merkel, and whatnot. And they were talking about how to reduce the carbon dioxide emissions, which are in billions of tons, okay, which released between 1750 to 2018. So this CO2 emissions, India is, very low in that regard. United States tops the list, followed by China, Russia, Germany, UK, Japan, and then India. So we must understand what is this net zero effect. So look at this particular chart, which I'm showing here. I have deliberately shown the year 2020, and this is January 2020. The atmospheric carbon dioxide concentration, according to IPCC, was 410 ppm. And you know that most of the 2020 was, all activities had been curtailed, and so you will assume that the carbon dioxide emissions would have gone down. On the contrary, what had happened that instead of 410, it became 412. So we added 2 ppm of carbon dioxide during the year 2020. So that is astonishing. And what it means that the nations of the world, the so-called Paris Accord or Paris Agreement of 2015, where nations of the world said that we would bring down the temperature of the globe by 2 degrees Celsius, by the year 2100. Majority of them said that if we could curtail carbon dioxide emissions and go to non-carbon based energy sources, the temperature could be brought down to less than 1.5 degrees C. Supposing there is no technological intervention across the world, imagine what catastrophe it is going to present to us. In the year 2050, the temperature of the globe would have gone beyond 6 degrees C. That means the glaciers will melt, these coastal areas will be sunk under sea, and it will be a disaster for the world. That means we have to take action right now to stop this disaster. So why it is happening? It is because of carbon. So carbon as a source of energy has advanced the societies of the world. The civilization has increased. Our comfort, luxury, etc. is because of carbon. Although carbon does not contribute much in the entire world scenario. The maximum is oxygen and then silicon. But carbon is the source of economy. So when you have a carbon-based economy, on one hand, which we all are familiar with, the so-called non-renewable or fossil carbon sources, and in which we have oil and natural gas and coal. And you know that during the beginning of the 20th century, majority of the chemical industry was based on coal, and Germany was at the forefront. So now what is happening? Coal consumption has not gone down because coal is used for making power. At the same time, oil and natural gas. So I'm going to give a little bit of history to put everything in perspective. And we have on new finds of oil and natural gas. So gas to liquid processes, and now they are talking about crude to chemicals. In fact, major companies like Reliance in India have announced these CTC plants. So we have coal to gas and coal to liquid processes, and it is here where we talk about clean coal technologies, the underground coal gasifications, where you can take it to syngas and then from syngas you have Fischer-Tropsch synthesis and you make variety of chemicals and fuels. On the other hand, in the case of renewable carbon, which you know that biomass, so this so-called bio-based economy, you have still processes which are based on chemical conversion, which could be catalytic, non-catalytic. Then you have biochemical conversion, and the last one is the thermochemical conversion. So here in chemical conversion, you can have direct conversion of biomass into chemicals, or you go through the so-called biochemical processes where you have fermentation or enzymatic conversion of biomass. And in the thermochemical processes, you can directly convert biomass into gas or biomass into liquid. So these are very interesting things. What happens ultimately? What is the fate of carbon in the atmosphere? Whether you source your carbon for the non-renewable resources or you source it from the renewable resources, it ends up as carbon dioxide, and which must be tackled to reduce global warming. So the so-called climate, summit, which was held in April 2021, was talking about it. We have analyzed this, in our paper, which we published in September 2021. This paper, where we talk about a choice between crude oil and biomass versus sustainability and the environment. This paper has more than 4,000 downloads since it was published. So many of the people who are planning, so this includes many countries across the world like Canada, USA, this paper has been downloaded. So what it means, the savior of the world is hydrogen. So I'm going to talk about hydrogen and why hydrogen is a savior. So you can see we have a savior if you believe in some philosophy or you have your own faith and you say it is your deity or God. So according to me now, hydrogen is going to be our God. And why it is going to be our God? Because it is going to save us from disaster. Like we always pray God saying that, God, please save us from disaster. So what happens, I mentioned to you that why hydrogen? Because hydrogen is the cleanest fuel which can be produced from hydrocarbons or from water and can be used to convert carbon dioxide into useful products. And the treatment of biomass, whether it is virgin or waste, into hydrocarbons with the help of catalysis. So catalysis plays a very, very important role in converting carbon dioxide into chemicals, fuels, and materials. So this hydrogen can be derived from hydrocarbons. So there are many, many processes, or it can be derived from carbon dioxide. So I'm going to talk about, why hydrogen is going to be a savior, and I'm going to give you some interesting aspect. In fact, I wrote this article on the case of hydrogen economy as a guest editorial, and before that in the Millennium Post, which is published from Delhi. In Current Science, this case editorial has appeared on 23rd of March. So I mentioned to you, whether you have a petroleum-based industry or you have a bio-based industry, what it means that you have carbon dioxide, and this is the cycle which we know, petrol or coal, and we convert that into chemicals, fuels, and materials, and ultimately that goes into carbon dioxide. That is also true for bio-based universities. So what it means, can we valorize carbon dioxide so that the global warming is reduced and we have the so-called net zero industry? So what happened? Because of COVID, many things happened. The manner in which we are interacting with each other right now, this would not have been possible. Professor Basu mentioned that my visit is due. In fact, I have been coming to Bhubaneswar because of my ICT IOC center there. And so when things become normal, definitely I'll be there. And also the ChemCon 2021, I hope that it will be a physical meeting if everything goes well, and I'll be definitely there. And of course, I would love to give lectures, including, teach some basic concepts in chemical engineering, catalysis, and whatnot. What happened before this COVID? Already Russia and Saudi Arabia were fighting for the price of crude oil because they wanted to get chunk of money. And during that time, because of the corona, it so happened that there was a negative price of crude oil, to be precise, on 10th of April 2020. What is the meaning of this negative price? That means you produce more and you don't have, storage place. So you have to pay somebody to store your crude oil. That is what the negative crude oil price means. And it happened. Then slowly it recovered. It went to $12, $18, $31, $32. And the pundits who are talking about the oil economy, they say that the minimum price should be $45. In fact, many of them say the comfortable price for the oil industry to be viable is $60 per barrel. And today is about 70 plus US dollars. So what effect it had on fracking on the energy industry? The fracking business is affected to the level of extinction. And fracking is, like fracking in Pennsylvania or Houston, Texas is very well known. 7 of the most active companies in Texas have already cut down $7.6 billion from their budgets in response to this ridiculous oil collapse. And remember, our consumption is about 97.4 million barrels per day. So you can see it will hover around about 100 million per barrels per day as the population increases. So this is where I'm going to show you something which may be known to you, but for the understanding of others. See, look at this is the left-hand side is the the typical crude oil refinery. So you have a crude oil refinery, then you have atmospheric distillation, and then you can see what happens, and all these processes. Everything in this crude oil, these refineries have the maximum atom economy. That is what they said. Although they process something like 1 million to 10 million barrels per day. It's very high capacity. But see the number of places, including the hydrocracers or isomerization or hydrotreater or catalytic reformer, wherever, or FCC feed hydrotreater. You see how many places hydrogen is used in this refinery to add value. In fact, the same concept is used in the case of the so-called bio-based, bio oil or whatever. Unless hydrogen is used, you cannot add value to that product. And where do they get this hydrogen from? They get this hydrogen from, natural gas steam reforming. So there is always the co-product carbon dioxide, and now they don't treat and it goes into atmosphere. So this is the so-called gray hydrogen, because the hydrogen comes, but carbon dioxide also comes. This is very cheap. For example, this could be about $2 per kg. On the right-hand side, we have this bio-based feedstock. You see that where you could have industry waste, you may have biofuel crops, or you may have agricultural waste, or you could have oil crops. And all these things, and you have the so-called 2G biofuels, like cellulosic bioethanol, biohydrogen, synthetic biofuels, and whatnot. Even in all these cases, the value of biomass goes up, and all these products, we have published a number of papers where hydrogen is used to break those molecules and take them to a much higher value. Sometimes you have to remove oxygen from this. So there is another in the so-called biorefinery concept. You have biomass, you will have a sugar platform, which is C5 and C6, and you can make a host of chemicals and fuels. Or you have the syngas platform, which is the thermochemical process, or there you could have combined heat and power. So what it means, hydrogen plays a very, very important role, whether you are talking about the so-called currently available technologies, the refineries technology, or the biomass as a feedstock. And I've already mentioned that in refinery processes, these are the places where hydrogen is used abundantly, like cat cracking, hydrotreating, hydrocracking, cat reforming, and the so-called HDS, HDN, and HDO and HDM, where hydrogen has to be used to add value. And so this is very, very important. A lot of catalytic work has been done in this area. So if catalysis was not there, the refineries would not have been able to make money or give clean atmosphere. So what it means, the energy and environment are intimately connected. And we know that the climate change is because of the overuse of these fossil fuels and also because of the so-called greenhouse gases. And the energy needs of the world are increasing day by day, and therefore the carbon-based fuels will continue to rise. And what is believed by 2030 and particularly by 2050, can we make a net zero economy? Okay, so that is what is. So the basic question now, so I'm going to have a teaser, some sort of, should biomass be wasted on making low value, high volume biofuels? And instead, can we take biomass directly to chemicals and materials? So I'm going to justify my thesis by saying that biomass should not be used on making biofuels. So this is contrary to the government's policy. Government's policy right now is to make bioethanol from agri-waste, etc. My thesis is no, you do it for some time, but in the long run, it should not be used to waste. Carbon should not be waste in making fuels. Otherwise, we will not be able to achieve the net zero economy. So look at the carbon-based economy. We, since 1980, you see, we have contribution of various non-carbon-based, economies also, like the energy sources, like non-hydro renewables, hydropower, nuclear power, and here the carbon-based, we have coal, natural gas, etc. So it is increasing, and the projections show that it will increase. Now, this is very interesting. So no matter what we use at the end, we have these finished products and consumer goods. This is based on a simple thing. You take very cheap raw material, that is petroleum or coal for that matter, natural gas, air and sulfur, and you make all sorts of chemicals. So there may be commodity chemicals, secondary commodity chemicals, intermediates. This is what the typical refinery does. And this is where the contributions of chemical and allied industries to modern society are reflected. Whether it is the requirement of fuels, energy, materials, basic needs, add to our luxury, comfort, or quality of life, carbon has played a very, very important role. And so I'm going to tell you some historical perspectives also. Ultimately, how the carbon comes and from where it comes, we need these finished products or consumer goods. So let us look at, and last year the government said we will stop import of Chinese goods. It is easy to stop import or ban apps because, they are based on electron, right? But you cannot do immediately for large number of these, molecules, the feedstocks, the APIs, which come from China, because without that, we cannot do anything. And we have realized that, when we realize that United States is not giving us the raw materials, so the Serum-Institute was able to make a vaccine. That means we still require some raw materials coming from abroad. So to make India self-sufficient in Atmanirbhar Bharat, that is the whole idea. So it is going to take time, but we have to develop technology on our own. So what would happen in the year 2054? And I have chosen this year based on literature. One of the literature which is very important source of, for energy related research is BP Energy's annual reviews of energy. But BP Energy says that, by 2054, we will not have any crude oil coming from Mother Earth because the technologies will not be viable. It is not that all crude oil will be exhausted. No, that cost of extracting the crude oil will not be viable technically or economically. So a lot of crude oil will be left behind. And it is known that if those of you who know about, the oil recovery and enhanced oil recovery, a lot of crude is still left behind in the and that could be anywhere ranging from 30% to 70%, depending on the pore structure, the type of rock, whether it is a carbonate rock or a sandstone or whatever. We know that. And so, and very interestingly, if that is the case, what are we going to do for our material and energy needs? Okay, so there are three energy scenarios. And what is that? In the year 2020, something like 35 gigatons of carbon dioxide was emitted in the atmosphere. And this has to be reduced in the net zero economy by 2050. That is where all the nations of the world are wedded to that particular idea. That means it has to be brought down below 10 gigatons of carbon dioxide. How do we do that? So there could be a rapid transition, or there could be we don't bother and we say that is the scenario which I showed you about the carbon dioxide emissions earlier. So yes, for below 2 degrees C, this has to be about 20, and below 1.5, it has to be less than 10 gigatons. So what it means, the share of the renewables, and these renewables will include wind, solar, geothermal, biomass, biomethane, biofuels, whatever, which of course excludes the large scale hydro dams. So what it means that from today's scenario in 2018, for instance, that is the reference, this has to go down. And if you want to have a net zero by 2050, this has to be a rapid transition. So of course, Government of India is also talking about electric cars, isn't it? So what it means, the share of these renewables has to increase substantially, and it has to go beyond 60%. And so how that is going to happen, so I'm going to show you. So remember, over the years from the year 1900, we see that we have increased in, so we have some new finds of natural gas, the renewables will increase, the consumption of coal will go down, and oil had peaked here and it will go down substantially. That is what the changing global scenario. So I already mentioned to you that we have something like 97.5 million barrels per day of oil consumption, right? That was it. And so that has to be brought down. So where does this oil go? So there are many things. There are transport section, this transport will include aviation, railway, etc. Then there are trucks, okay, there are cars, and there are other non-transport. And then non-transfer includes heating of buildings and whatnot, okay? So there's the so-called housing sector. It requires a lot of this. And remember, natural gas is also supposed to be so-called, net zero economy. Okay, that is what, is argued. So natural gas finds, new finds will be explored, and we will have some contribution. And so that is there. So in net zero, natural gas is also going to contribute. So this is so-called near zero carbon energy. So with natural gas has to be coupled with carbon capture, utilization, and storage. Remember. So when when it is not there, so that is what happens. Like currently I showed you in the earlier slide that natural gas is used to have steam reforming to get hydrogen, and the carbon dioxide is not captured. So that is not good. So in the net zero economy, so we have a blue hydrogen, we have a gray hydrogen, and we have a green hydrogen. So in the blue hydrogen, you take carbon dioxide emissions and you stop them, okay? You convert into something else. And so I'm going to talk about that. So yes, you can see that. So whether in the net zero by 2050, you see, so we have a contribution of geothermal and biomass. Solar and wind are going to be our saviors. And you know that India is the chairman or the chair of the Global Solar Alliance, right? And we will have a lot of this, solar, energy. That is good. So what is going to happen? The cost of the solar energy or the wind energy will go down substantially. So as a result, we will find that, so you see the hydrogen, power, building, industry, transfer. So by type, and this is by sector. So in the rapid and net zero economy, so it is very, very important that we have biomass, we have biofuels, biomethane, and at the same time, hydrogen. So hydrogen contribution by 2050 will be about 24-25%. So because of this, continuously declining prices of solar energy, you will see that the investment in that, afterwards the industry will get matured. So the investment will go down, but it is good for the world as a whole. So we have these three types of hydrogens, which I mentioned. The green hydrogen, where electrolysis of water by using different techniques. So maybe you will have clean electricity, and the electricity is produced from wind, solar, hydro, nuclear energy. So that is a gold standard, having zero greenhouse gas emissions. So green hydrogen is the one which is the savior of the world. Then you will have blue hydrogen, where steam reforming of biomass, wherever there is a carbon, you do steam reforming, you can produce hydrogen. Okay, that is as simple as that. So we have biomass, the bio oil or natural gas, and it will give carbon as a carbon dioxide. So you have to have captures up to 90% of the carbon, having low to moderate carbon intensity. And in the gray hydrogen, which is the currently practiced route, the steam reforming of fossil oil, fuel, coupled with cogeneration of carbon dioxide. And this method is the most commonly used technology. And this is no good for us in today's world. So yes, hydrogen by sector, I mentioned to you that, so in the industry, the buildings, there will be a lot of contribution. The hydrogen will contribute a lot. So, and what sort of, I'm going to give you some information little later, that the hydrogen production, you see that blue hydrogen and green hydrogen, these will be the major sources by 2050. So in short, this is what even, in fact, I argued in my editorial in Current Science. So this is based on the information provided by European Union, International Hydrogen Council, and Bloomberg, the new energy fund. And this is the hydrogen growth from 2% to in 2018 to about 13 to 24% by 2050, and the CAGR will be about 8%. And this is what so there will be $150 billion investment. This will increase, but this is the figure which is told about right now. So yes, so for hydrogen economy to be a reality, hydrogen must be produced cheaply and in an eco-friendly manner. And so the net zero economy, green hydrogen will have the dominant role to play. So yes, in other words, what it means, if you have a global, because the global energy scenario, we will have more need for energy as we go along. So you see by 2040, see more energy, primary energy, and there is so less carbon dioxide, and this is what is desired. Okay, so we want to have less carbon economy. So this is where we talk about the so-called world scenario. I already told you about this, about solar, wind, hydro, nuclear, gas, and coal. Remember, by 2050, still will be using coal. It is not that the coal-based power plants will be still there. So yes, so from 27% to 51% from 2035 to 73% by 2050, with total energy requirement of 49,000 terawatt hour. So as a feedstock, there are numerous potential applications, various industry, transport, power, building, and since there is no carbon dioxide, this is the best. So this so-called decarbonization of industry will be done by the hydrogen. So, and the carbon will come from, renewable sources, maybe biomass, okay, for example, or whatever carbon dioxide goes in the atmosphere is converted into chemicals and materials. So, but at the same time, since I'm little bit interested in history, and this is what we have given in our research paper, which was published, and I told you it has huge number of downloads from there since we published it. In the earlier industrial societies, there is a term which is called as well oileries. So instead of refinery, they used to call oilery. So during the 18th and 19th century in the North America, they used well oil in oil lamps and also to make soaps. So the whale oil was obtained from the blubber of the whales. So that means you have to capture whales, kill them. So what happened? As time went by, the population of whales in the sea decreased substantially. So almost it went to extinction. So you can see this is the old picture, and you see the oil, how it has been produced here. So this was the source of, energy and making soap. So this is the time when we have the most, interesting part in the history of mankind. That is the birth of the oil industry. Okay, this picture we have drawn, and this is taken from my paper. So I will enlarge this. So see the birth of oil industry. We must thank this Colonel Edwin Drake, who drilled the first well in Tutusville in Pennsylvania. And as they say, rest is history. So 1860, you see, so there were few more oil wells. In India, it was about 1895. Okay. So what did they do? They had this petrol coming out because they used to, distill it, crack it, maybe, thermal cracking. And there was no use for this gasoline or petrol. So what did they do with the petrol? That was just let go in the rivers and the streams and whatnot. It is a laughing matter, isn't it? What they used only was kerosene part of it, and the heavy oil and the residuum was used to make, roads and whatnot. However, thanks are due to Henry Ford. In 1907, he introduced the first automobile, and it changed the face of the world. And there was a dramatic, consumption, increase in consumption of oil. Then the First World War came, and during 1920s, spectacular advances took place in the process, evaluation of this oil, industry. So you had thermal cracking, you had atmospheric distillation, vacuum distillation, VGO, name it, naphtha and whatnot. And this is the time also they had this so-called clay catalysis. Clays were used. Howdrey was the person who. So we can see that gasoline, kerosene, petrochemicals, kerosene rather, and petrochemicals, this was the period, most interesting period in the history of mankind. One of the persons, I must mention this, sometimes history tells us what wrong things we have done even in science and technology. There was a gentleman called Vladimir Ipatin. He was a general of the Soviet, army. He retired at the age of 60, but he was a scientist. He was a great scientist, and he was a catalysis scientist. All these things, whatever we have derived benefit from the petroleum industry, is because of this guy, Vladimir Ipatin. So he just after his retirement, he went to Germany. By train, he told his wife, you just look at your whole mother country and say goodbye forever. But he was also a romantic man. So this UOP hired him and took them to, he did not know a word of English. He only knew German and Russian. But he was a romantic man. He has a concubine also. The UOP also hired the concubine as well, took the concubine. He went to the United States and did spectacular work on catalysis, this reforming, platforming, and name it. He was nominated for Nobel Prize, but the Nobel Committee felt that he was a military general. He was, associated with crime. He was never given Nobel Prize. He had nothing to do with that. Sometimes we have many cases like Dmitry Mendeleev was never given Nobel Prize. So Ipatin, I feel, and this is given in the history by UOP, which is, the title is a very interesting book they sent to me. I got it from Singapore. I requested them. That is called Ideas for Rent. I read that book in a single go. It's such a fantastic, book of history of, this oil industry. So you can see that in the 1940s, because of the Second World War, there was a surge in oil production, and there was better technology. And this is where, this alumina silica catalyst was used. Okay, first time. And the quality of fuel, of the aviation fuel by the Allies was far superior than the Germans. And that was the singular reason for their victory. Very interesting. Nobody knows this, but this is recorded. In fact, I have given us a reference in my article, how it happened. So you can see and in 1960s, we had geolites. And then you get all these, none of the refineries now were without FCC and the geolite, ultra stable Y and whatnot. So you can see that the various kinds of value-added products. Okay, this is called a spread. In Euler's terminology. So you see the industry grew like anything. So the catalytic polymerization, visc breaking, and solvent extraction, solvent deasphalting, cat cracking, FCC, etc. These were all advances, and now the refineries are most complex. Safest industry, continuous industry, highest use of catalysis, minimum wastage of carbon. That is what refinery is. However, because we are talking about net zero, we have to go to the so-called bio-based products and not the fuels. So we can make a lot of these chemicals, and these are the feedstock which many biorefineries which are planned and under development across the world. You can see the kind of products like propanediol, butanediol, 3-hydroxypropanic acid. One of the most important is hydroxypropyranol, HMA, hydroxymethylpropyranol. Of course, hydrogen. And these phenols, your vanillin, xylitol, name it. Fantastic, products which can be made instead of wasting carbon on, ethanol. So we also did analysis of the network of transport pipelines. We don't have, unfortunately, this kind of data available in Indian scenario. Then we looked at this, and these are the published data. And so we can see that we have so-called bioethanol plants, biorefineries, and corn-producing regions, and shale and oil gas deposits. You see that this is a very nice picture which is there in our paper. And you see, so this is so-called crack spread. What is the meaning of crack spread? When you do cracking of the crude oil, so supposing your dollar, barrel cost now say $70. The crack spread means what is the value of the all products which are made from that. It has to be not less than $80. Okay, that is the spread, crack spread. So we found that we could, suppose we take 1 kg of crude oil, what it gives us is 32 megajoules of fuels and about 0.2 kg of chemicals. And if you take analogously 1 kg of the biomass, it gives us only 6 megajoule of fuel and 0.8 kg of chemicals. And you see that this chart itself shows that making chemicals is a better idea. We argued in our paper than, in fact, the referees of this paper, we had submitted this paper to Nature. And one of the editors was very critical. He said, no, you're talking something which is, but anyway, we published in another journal. But I'm telling you, and everybody is thinking here, what we said is absolutely correct. So now you see, so suppose I gave you something like 97.5 million barrels per day. And suppose we take that as a reference. So, and if you take crude, okay, how much we get? Conversion of chemicals are $215 per barrels per second. If you take 100%, we can get the corn or the biomass, we get only 10 barrels per second, this energy. And here you see that we have, if you convert everything to chemicals, we get 320 barrels per second. And you add the value to that. So this particular chart shows that it is better to make chemicals than making fuels. And if you make fuels, you are wasting that carbon, as carbon dioxide. So what we did, we had a lot of data available from US Department of Energy. So we took that data, and these bubbles are giving the size of this industry, the investment. So without going to the details, this is the green one is the success and the red one is the failure. There are many biorefineries which have gone into biofuels. They have failed, okay, and they are currently on pilot scale. So this is giving a very interesting analysis. And so we said, supposing we have a petroleum-based products in North America, and there is a transportation fuel. So you see that bagasse, ethylene, propylene, styrene, butadiene, vinyl acetate. Remember how many megatons per year are produced. So then another thing which we talk about is methanol, because even our Niti Aayog is talking about methanol-based economy. So we looked at this aspect also and look at the carbon efficiency and the thermal efficiency. Carbon efficiency is 0 per hydrogen, as is very abundantly clear, and you go over here. So and the steam, the reforming. So we have methane conversion, MTO, methane to olefins, or oxidative coupling of methane, and they have higher thermal and carbon efficiency compared to a steam reforming, cracking of ethane, okay, steam cracking of ethane. And the bubbles in this, of course, they show the current capital cost, and the white part here is showing where this will be viable, and this capacity is taken on the basis of today's requirement, something like 12,000 barrels per day. Okay, So if you do methanol economy, whatever the source of carbon coming from, maybe it is clean carbon coming from coal or the carbon coming from carbon dioxide and goes to methanol. So you can see all sorts of things we can make, like dimethyl ether. Dimethyl ether is a very good substitute for LPG and diesel. So there are all sorts of chemicals we can make in the methanol economy. And we also compared the so-called levelized cost of electricity, which is where we use the generated by combined cycle power plants, fueled by natural gas, and this is much lower than either where you have the natural gas. You can see that the vertical line here shows the average levelized cost. So you see for biomass over here, you see for natural gas where you have combined cycle plant. So this also shows that level of cost electricity is much lower for natural gas when you have this combined cycle power. And we have a catalog of catalytic processes to make chemicals, and so we have, and all of these things are catalytic processes. My lab, we have worked many of these processes. This is just to give you a glimpse that when your sugar alcohols or your furfurols or your cellulose, hemicellulose, and lignin-based chemicals like vanillin, syringaldehyde, vanillic acid, and whatnot. So for example, so you have biomass, you treat it, you get cellulose, hemicellulose, lignin, and you see all sorts of products can be made. And a lot of work has been done in India. Many people are working here as well. So you can see xylitol, furfural, sorbitol, livolinic acid, ferulic acid, and all those things can be made. What is important? When you have carbon dioxide, nature's photosynthesis, you get oxygenates, or you have carbon dioxide reduction with hydrogen, goes to hydrocarbons. So methanol, dimethyl ether, formic acid, some of these products, hydrogen is the key. And at the same time, we have another interesting aspect, the plastics. I've written an article on this also. For example, this plastic, whether you have PET, HDPE, PVC, LDPE, polypropylene, all these waste plastics can be converted into fuels and chemicals by using hydrogen. So we have plastic additives, you have functional additives, you have colorants, you have fillers, reinforcement, what it means your organic and inorganic materials. So if you look at the waste plastic recording techniques, we have something called chemolysis, chemical treatment, or thermolysis, thermal treatment. And you see that chemolysis, pyrolysis, gasification, these are the technologies which can be used on waste plastic to convert them into valuable products and reduce pollution. So in chemolysis, we have hydrolysis, glycolysis, aminolysis, alcoholysis, and acidolysis. So hydrogen is, so whenever there is a pyrolysis product, fuel oil, because a lot of people, even India also, people have written papers on that, but that is a poor quality fuel oil. It cannot be used, directly in the engine. So you have to treat that with hydrogen. So advantages of plastic hydrogenation, high value product, and we can handle troublesome atoms like chlorine, nitrogen, oxygen, and sulfur, because these are the technologies which are already existing for refineries. We know it, that technology exists, so we don't have to reinvent the wheel. So yes, so we have hydrogenation reactions. You have the cracking function and the hydrogenation function. Those who are working in catalysis, you know that there is a dual functional, and we can develop different types of catalysts. Yes, so HDS, HDN, and hydrodeChlorination. So we have PVC, PET, polyamides, including rubbers, all these gases, these can be handled in the refinery. So the plastic waste is the best way to be handled by using hydrogen. So of course, you require new kinds of materials. And when we were developing our own technology of hydrogen, we realized that we have to do research in materials as well. And we have done that. Okay. So let us look at the India's total global primary energy demand. And between 2070 to 2040, 42% of this will be through coal. That means CO2 emissions will roughly double by 2040. And we have signed an agreement of net zero. So how are you going to do that? So remember some statistics, 156% growth in Indian primary energy by 2040. 11% will be the share of India in the global energy consumption. 58% of the share will be from coal in the power mix, and 116% growth in India's net CO2 emissions by 2040. And in the case of renewable energy, see about 20 million tons of oil equivalent to something like 300 million tons of oil equivalent by 2040. And this will be mainly concentrated in power sector, okay? And that is because of the solar energy. And you know that the solar energy is going to be a savior along with the wind energy. Okay, so still, despite this, there will be still coal-driven power plants. Okay, and this is where hydrogen, once again, as a carbon-negative source of energy, plays a very important role. And I need not sing any ballads in the praise of hydrogen, the cleanest fuel. But we know that once you are hydrogen, you can have, hydrogen vehicles, synthetic fuels. You can upgrade the oils, including the plastics, which I mentioned to you, or ammonia, or metal refinery, or the many other fuel cells, etc. Electricity generation, heating, and you can see that you can generate power and it can go into the grid. So hydrogen is going to be our savior. So, okay, and so there are many methods of hydrogen generation. So what did we use? For example, this is another interesting thing which is given by McKinsey. So power generation, transport, industrial energy, building, heat and power, you see the share, the market share by 2050. Okay, so vans, minibuses, carbon capture units have to be utilized. There will be use of methanol. Then all sorts of things. The bubble size again indicates the hydrogen potential, 2050 in exajoules. So ammonia, methanol, refining, you can see that it is still there. And so you see from 2015 to 2050, look at the number of, so you see 63%, 63, million metric tons. Okay, will go in power generation, 154 million metric tons in transportation, then industrial energy, 77 building, and carbon capture and new feedstock, and 70 will be the existing feedstock. So since you are connected with minerals and materials, so whatever we have, when we use the store, for example, if water electrolysis, you get hydrogen, it goes into the iron industry and you can make steel. So this is very well known. So this is green hydrogen, or you may have natural gas. Okay. So there are continuous improvements made across all hydrogen technology. And you see that this particular slide shows the hydrogen cost in Europe is now between 2 to 4 euro per kg. Okay, this is what it is. And the high capacity is increasing. So you have hydrogen storage, you go to fuel cells, or you have the hydrogen fueling station. So what is required, like when the petroleum industry was in the infancy, we had to build a lot of these petrol pumps. So their infrastructure was required. So if we have hydrogen as a fuel, we require hydrogen as infrastructure, the pipelines and whatnot. So yes, so what we did, this is our patented technology, ICT Mumbai, ONGC, the Energy Center, hydrogen production, because they supported my research. Since 2006, they have been supporting. Our hydrogen is produced at 95 cents, which is much cheaper than any other, and the co-product oxygen, we are not valorized it. So oxygen is very important, because of this COVID situation. But even otherwise, oxygen is also another, reagent which will add value to this biomass, waste biomass. So hydrogen and oxygen. So in other words, in our technology, we have coupled solar energy with molten salts. So during night, that there is no solar energy. So we have molten salts where the energy is stored and that is used along with water. So once again, water is a feedstock, no carbon feedstock. And why hydrogen? If you compare the age-old wood, which is from antiquity, through ethanol, coal, biodiesel, etc., hydrogen has the highest specific energy. So hydrogen beats everybody else, okay? And so we have hydrogen production from renewable energy, nuclear energy, or fossil fuels, okay? So in nuclear, you have radioactive waste. Here you require energy input, and mostly it is steam which is required. You crack or steam reforming, and you have to do carbon sequestration. Somehow you produce hydrogen, and that has to be stored and utilized. So what happened? We worked on large number of, these are some of the papers, including the patents. You know, these are some of the papers which we published on blue hydrogen processes. So what it means that you take natural gas, propane, biomass, or wind and solar, or uranium, you produce hydrogen and you store it. That is what I said. So mainly thermochemical processes, maximum is the natural gas steam reforming, 95% processes. Then biomass gasification, or you have PEM electrolyzers, or you have photoelectric. And in the case of biohydrogen production, this is fermentation or biophotolysis. So these are 4 different types of methods by which you can produce hydrogen. Or you have a solar hydrogen. See, once again, you use CO2 pool or biomass pool, and you can see that once you convert to carbon monoxide, then you have methanol, then you have gasoline and hydrocarbons and methane and whatnot. The carbon dioxide can be converted into methane. So if you look at the industrial hydrogen production, steam reforming is 48%, oil naphtha is 30%, coal is 18%, water electrolysis 3.9%, which is less. And this is where people are trying to concentrate now. So if you compare the reforming technologies, steam reforming has been practiced the maximum, but it has highest air emissions, right? The carbon dioxide emissions, then autothermal, and then partial oxidation. So what we studied is the thermochemical water splitting for green hydrogen. So we had studied a lot. ONGC gave us money to study, sulfur iodine cycle, but then they said we should concentrate on copper chlorine cycle. So ultimately we had done initially work on this also, but we found copper chlorine cycle was the best. So you see, so steam reforming commercially 70 to 85%, biomass gasification also commercial, alkaline electrolyzer also commercial. So the blue ones here, they are current mature technology. Okay, and sometimes you get byproduct hydrogen, like this alkali industry or iron industry, and you see these are future technologies. So we are working in this group. Okay, and so what we did, we compared our processes with the published literature and the reviews. So steam methane reforming. So you see the cost of hydrogen $2.27 per kg. The investment in $1 million. It is given, and the source is natural gas, coal, etc., or water and algae. You can see lowest you can go is up to 1.59 or 1.225. This is biomass pyrolysis. So we have photofermentation also. We have solar photovoltaic also. So you see that, and the last is our process, which is solar for thermochemical. We produce at 95 cents. So this is very exciting, and so we are now commercializing this with pilot plant with the help of ONGC. And so there is a life cycle analysis of so-called well-to-gate greenhouse emissions. For green hydrogen, it is 0, right? Steam reforming of natural gas is 9 kg carbon dioxide per equivalent 1 kg of hydrogen. Steam reforming of natural gas with carbon capture and storage with their capacity, say 90% or 56% will be 1 or 4. So this is less than that. And natural gas price in the European Union, which is published here, is about $26.8 per megawatt hour, and electricity will range anywhere between $40 to $100, and capacity cost is about $730 per kilowatt. So one of the things which is going to be a very important parameter, those who are interested in the electrolysis, the electrolysis laser costs have currently they are about $1,100 per kilowatt, and they will reduce by 2040 to about 550 to 220 mid 2030, so 220. So almost 1/5 it will go down. The cost of carbon capture, of course, increases the cost of steam reforming, and so this will be $990. And low carbon based fuel hydrogen will be about $2.5 to $3, and green hydrogen 1.2 to 2.9 kg. And so that is what they say in the net zero economy. So the target for solar electricity has to be cost competitive with the current fossil fuel system. And if the cost of the installed PV power can be reduced from the cost of something like $5 per watt installed capacity to something like $1, that means 20%, then the cost of electricity will reach about 0.1 per kg per per unit, right? 0.1, which is about say 8 rupees. So yes, so what it means, the future cost of electrolytic hydrogen, small plants is about beyond 4. This includes the operation and maintenance. With a large plant, it will go down beyond 3.2. Future continuous about this, and this is what the US Department of Energy said. If you bring down the cost of hydrogen below $2, that will be highly economical. And this is what, so by 2030, hydrogen economy will be the, the buzzword. So that is what I wrote in my editorial. I said that government of India should go for hydrogen economy. In fact, I also wrote to the principal scientific advisor. So what we have done in our laboratory, and we are doing it, and this work is still going on. So we have combined solar power with molten salt. So we have got patents in the area. We have taken copper chloride. We feed water. We get hydrogen. We get oxygen, which can be both used for conversion of carbon dioxide into methane and hydrocarbons, or use hydrogen for waste biomass, or use hydrogen for making hydrocarbons, methanol, dimethyl ether, formic acid, format, syngas, ammonia, fuel cell, hydrogen vehicles, electricity, name it. So that is so this was one part, this is another part, and this is the third part. I am very happy to tell you that we are transferring one of our technology, which was then independent of ONGC, the dimethyl ether technology, to one of the industries. In fact, after the pandemic is over, this plant will start. Okay. So this novel catalytic technologies must be developed in near future to arrest climate change and carbon footprint, and the goal of our ICT's efforts are in that direction. Okay, so yes, so finally what it means, we'll have new hydrogen applications. We will have existing hydrogen applications like steel industry, ammonia, methanol refining, biomass conversion, and you will have low carbon competition. This is what is going to happen in future. Then we will have heat pumps, all sorts of things will there. There will be many, new applications which will come in as CUVs, mid-side, small range vehicles, syn fuel, aviation, name it, heavy duty trucks. So hydrogen will be the real savior, like our God, which is what I told you in the very beginning. So finally, the so-called question of linear versus circular economy, hydrogen will again play a very important role, and I gave you example of plastic. So to conclude, the notion that biomass per se can replace oil as a feedstock for fuel and chemical manufacture was critically analyzed by us in our paper, and we also gave all sorts of viewpoints. So biomass is chemically and geographically incompatible with the existing refinery and pipeline infrastructure in most regions. Biomass should be used for production of valuable chemicals and materials and not as a source of fuel. That we proved through calculation. Using crude oil, biomass, and shale gas to produce fuels, value-added chemicals, and commodity chemicals, respectively, is a better prospect than using biomass exclusively. Using methane as a feedstock for the production of methanol also lays strong foundations for the future methanol economy. Hydrogen economy can be elegantly intertwined to make many chemicals from waste carbon sources, including biomass and C1 of gases. So the government of India should adopt hydrogen economy to meet the demands of the Paris Agreement. That is the only way to meet the goals of Paris Agreement 2015, to which we are signatory. So I must thank all my research group over the years. And yes, so this, apart from this, so yes, I still have 15 PhD students working with me. And this is what, what we have done. So thank you so much for listening to this lecture. And I once again wish you all the very best for the occasion of this National Technology Day. And I just told you a story which has an international perspective, and also what we did in ICT and what government of India should do. Thank you once again, Professor Basu, for inviting me. It was a joy and pleasure for me to talk to all of you. And I assure you that whenever things return to normalcy, I'll be there in Bhubaneswar to talk to all of you. Thank you very much.
Thank you, sir.
Thank you very much, sir, for this wonderful talk.
Thank you very much, sir.
This is the time we may take some of the questions or queries. So
Yeah, no problem. No problem.
Sir. So anybody would like to ask any question, please ask directly. I think it will be better.
I will ask first question.
Yeah.
It's excellent talk and overall scenario in the hydrogen. What is coming to us, and we know part of it. A part of it we have learned from you, from your talk. I would like to know in India. Of course, this is what world scenario. And mostly the data available in North America, and so your focus was on North America and other places. But in India, how you are looking at it, how we can transform all the oil companies, all the energy companies, all the steel companies. I mean, they talk about it. They talk about green steel, making steel from hydrogen. The power companies talk about high use of hydrogen in future, and as well as the oil companies. But we thought that they are doing much less than what they should have been doing. What is your thought about it? What is your viewpoint?
I tell you, very good question. And look, there is no option for anybody if you are going to reduce the temperature of the globe and our dependence of carbon has to go down. Hydrogen is the best source, and I gave you examples. And why we use the North American data, because they are available, and we could cite Indian data were not available. But at the same time, all oil companies are, in India, working on this aspect. One is there, of course, all of them have been working on bioethanol and all sorts of things. Or companies like GAIL and other companies, hydrogen is being talked about. And so certainly in future, because when there is no oil, what are they going to do? So this is what happens. Because when ONGC was supporting some of these fellows, those who don't understand science, they say, why are you wasting money on this hydrogen? So I jokingly used to tell you, a job is dependent on what we do. So it is better that we must invest in technology. I tell you, that is what by 2030, and Nitin Gadkari ji is saying that we will have electric cars and things like that, or fuel cells, technology, all those things. If we don't invest in this kind of thing, then we are not going to do anything. And so it is high time we do it now. High time. I know you have worked on fuel cells and all. I know that in IIT Delhi. So this is the requirement of the day. And I'm sure, after I wrote that article, in fact, I was called once to give a small presentation. I did it. But yes, there is a realization. There is a realization. We have hydrogen mission, you know that. And that is the finance minister has also announced some budget for that. I have been in correspondence with principal scientific advisors officers. That and there will be many more technologies, not just one technology. As you know, there must be alternate options for that technology. One single technology doesn't work. There is no magic formula. So I think we have to do that.
Okay, sir. The next question by Santosh Kumar Mishra, sir, please.
Yeah. Read out.
Santosh, sir.
Can I speak now?
My question was, how about the role of nuclear energy in hydrogen production?
Yeah, nuclear energy.
We have plenty of thorium.
Yeah. See, that is being talked about, even the BRC and all. So, we wanted, in our technology, we wanted a source of heat, right? And so we use solar energy. Even there, nuclear energy can also be used. But best is, in terms of safety and all, solar energy best. But yes, nuclear energy, yes. In fact, I showed in one of my slides that nuclear energy is also yes.
Next question.
So the processor you are planning can be scaled up with.
That is what we are doing now.
High density nuclear energy.
Yeah. We have got several patents also. I must tell you that we have got several patents.
Right.
Although copper chlorine cycle is very well known, we have modified that. and therefore we got patents. First patent I got was in USA, then Canada, then UK, then Germany, in Japan. So all those places.
So you are
Including
putting up a
Korea.
pilot plant, sir?
Yeah, pilot plant, yes. Now, now we are going to do it in Goa. We have been given a land, so we'll do it in Goa.
Great. Sir.
Okay, and now we'll next move to Dr. Bhagyadhar Bhoi, sir, please.
Yes, sir. Thank you very much, sir, for your excellent talk. It is really very good insight we found that our laboratory is also doing a lot of work on green steel. Once the hydrogen is produced in cheaply manner, like as you have mentioned, that solar energy will be most useful for making hydrogen, production of hydrogen economically, then our technology is ready to produce the green steel directly from iron ore and using hydrogen plasma technology. So thank you, sir. Thank you very much. And you have given a very good comparable things. All things you have compared and how you can go for producing hydrogen and all. It is excellent, sir. We are really thankful to you.
Thank you. My pleasure.
Next story by Dr. M.K. Dhar, please.
Unmute, please unmute.
Sir, unmute, please.
Yeah. Sorry, sir. Thank you, sir, for your nice presentation. In fact, I am from Environment and Sustainability Department, sir. In my department, people are working on chemical engineering aspects. But to my knowledge, sir, one or two questions just I want to enrich my knowledge from you, sir. One thing, as you told, that ethanol production from biomass, a lot of people have done, and people have done excellent work. Little work also I am doing in my lab. And regarding biofuel, to my knowledge, sir, regarding biofuel and the bioethanol, why it is not more popularized in India?
So anyway, if I get your question correctly, see, bioethanol, it is, a government of India has a policy of mixing it with the petrol or diesel, and and that was an incentive for farmers because they are burning and creating pollution instead of. But believe me, none of these bioethanol, 2G bioethanol technologies, 2G particularly, are commercially viable. They can be at the most taken as environmental pollution prevention technology and not making money. Okay. Fermentation, yes, but in future, ethanol should not be burnt. That's what I'm saying as a fuel, but convert that into ethylene and a host of products like the petroleum industry is doing. That should be the objective. Okay, not as a burning as a fuel. And you know that the cost, because ICT has a very big deputy ICT center where bioethanol is being produced, and we were trying to promote that. And oil companies also had signed MOU with us, but they did not go ahead because the economics is not favorable.
Yes.
Producing ethanol in 100 rupees a liter, what you are going to get out of it? You will get nothing out of it. In fact, we were talking about production capacity of 400 tons per day, okay, which will be about 1 lakh liters per day, about 1 lakh liters. But that all other things. And you know what happens in that? The lignin is not valorized. Lignin has to be valorized. Lignin must be converted into valuable products. Otherwise, it doesn't make a sense. So it becomes a huge investment. So that 400 tons per day was more than 1,000 crore investments. So that is why it is not viable.
Okay. Another one thing, sir. Just I want to enrich my knowledge. As you told, sir, radionuclear waste. We have been working on, sir, high-to remediation of cesium and strontium. So that technology we have developed. But what is about the radionuclear waste? What you told, sir?
The radionuclear waste has to be treated by using the current methodologies. No, say they have to be encapsulated and they have to be buried, and that is what they currently do. So the that is a very big issue, na, radionuclear waste.
Okay. Thank you, sir. Thank you for it. Thank you.
Okay, now we'll take actually only one question, the last question, since actually Professor Yadav will be having the next.
I have another meeting. Yeah.
Manas, can I have one?
Yeah, Dr. Sanjeev Das, it will be the last question. Please, Sanjeev, please.
Sir, it is a very interesting talk, and in fact, I know you from my PhD days from IIT Kanpur. So
oh my God.
So since I've been working a little bit some carbon dioxide storage and catalysis and little bit hydrogen storage, but we all know the potential of hydrogen. But you have really presented a very excellent way with very fantastic data. But the thing is that with the hydrogen, we have that the storage, because
yes,
we know the volumetric energy density of hydrogen is very low because of high volatility of hydrogen. Because yes, although it is a 3 times higher energy density than gasoline, but for example, if you want to store a 5 kg of hydrogen, you need to have a 50,000 liter tank at room temperature. Or otherwise, you have to cool down at minus 250 degrees centigrade temperature, or you have to high pressurize about 500 to 700 bar pressure. So this yes, also will include in the economy also when you are calculating something. So being experts, sir, I need to learn from you a little bit your opinion about this matter, sir. How we are going to tackle this also?
Very good question. In fact, one of the most technologically difficult, challenging, but solvable problem is hydrogen storage. People have been using, or sometimes they are making hydrides, okay, carbon nanotube, multi-wall, or boron compounds, and name it. But people have been using it. Yeah, but at the same time, high pressure storage, as you say, rightly say, one of the areas which people have been, right now there are buses being run in Korea and also in California, where they are using these hydrogen tanks. So what it means, you have you have to have these refilling tanks, hydrogen refillers at certain distance when you go from one place to another, right? So that has to be another technologically challenging problem to be solved, but people are solving it. And I'm sure nothing is unsolvable as far as human genius is concerned, okay? Mind is concerned. So this will be solved. Yes, there are problems because you have to compress and store and then take it, but it is solvable. So there are many ways by which can be done. Like for example, formic acid is a source of hydrogen. Formic acid can be used for fuel cells. Okay, methanol can be used for fuel cells. These are allied problems, but they're all solvable. Hydrogen vehicles is a reality right now. I'm telling you that also. It is being done. So that is another aspect of this hydrogen economy where it can be done. And see, hydrogen-based electricity generation. So once you have electricity generation, all other current technology, battery-based technologies can be used, isn't it? So this is what is the real important aspect of hydrogen economy is.
Thank you, sir. Thank you very much.
Okay, now we'll stop this session. Now I'll move to propose the vote of thanks. So indeed, it was an excellent and very informative talk by Professor Yadav. Hope everybody must have enjoyed it. On behalf of our esteemed institute, CSIR-IMMT, I feel great privilege to propose the vote of thanks. We want to express our gratitude to our honorable chief guest, Padmashri Professor Ganapati D Yadav, for accepting our invitation and sparing his valuable time with us to grace this special occasion with his presence. Thank you very much, sir. I express our sincere thanks to our beloved director, Professor Sudhasutya Basu, for his constant support and encouragement throughout in the progress of science and technology, and of course for today's event. Special thanks to our CNM department, HOD Dr. Satyajit Rath and his team for IT related arrangements for this webinar. So behind every successful program, the presence of our dedicated scientists, staff members, and students are always highly acknowledged. Last but not the least, thanks to all the listeners who are watching live to this National Technology Day celebration organized by CSIR-Institute of Minerals and Materials Technology, Bhubaneswar. Thanks once again to all of you for your kind attention. Thank you all.
Pleasure, and thank you very much for inviting me, and all the best. Okay,
Thank you,
bye
sir.
bye. Bye bye.
Thank you. Bye.